AI/ML workshop series, seminar series, I'm sorry. Today it's a great pleasure to have Lukas Ruff visiting from Germany, in particular Berlin. So Lukas is a third-year PhD student in machine learning in the group headed by Klaus-Robert Müller at the Technical University of Berlin, and does amazing research on anomaly detection, in particular deep anomaly detection, which is a pretty broad and important topic, as you'll hear about later. Lukas's research covers robust and trustworthy machine learning with a focus on deep anomaly detection. And he received a Bachelor of Science degree in mathematical finance from the University of Constance in 2015 and a joint master degree in statistics from the Humboldt University, Technical University, and Freie University of Berlin in 2017. So with that, let me just welcome Lukas and hand it over to you.
Thank you very much, Stefan, for the invitation and for the introduction. So it's my pleasure to talk today to you about some recent work that we've been doing in anomaly detection and sort of giving an overview of the field as a whole. And as a motivation, so in many anomaly detection tasks, the data and the complexity, the size of the data and the complexity of the data is growing. So for instance, applications such as in industrial fault detection, so here in quality control, finding defects or errors, for instance, here in this wood panels or in the screws or nuts, or for instance, in system monitoring of high performance computing infrastructure or intrusion detection in networks where you have large amounts of system logs, or fraud detection, where these days you also have a lot of textual data, or in medical diagnosis. So for instance, in CT scans that you see here of a lung, or histopathology images of carcinoma of metastasis. Yes, and so such applications have motivated the development of deep learning approaches to anomaly detection. And so my talk is based on a recent paper that we've been putting up together with Jakob Kauffmann from our group, Rob van der Molen, Grégoire, Wojciech, Marius Kraft, that both Stefan and I know well, Tom Dittrich, and Klaus as well. And the focus of this review was to give sort of unifying perspective on the recent deep approaches and connect them to the overall body of anomaly detection research. And as a overview, so this is a categorization of the methods that we present in this work along two dimensions. So the feature maps that they're using, so more sort of classic, traditional shallow feature maps, so kernel methods and deep methods. And we have grouped them by common principles that are based on one-class classification, probabilistic or density estimation methods, and reconstruction methods. So this just as a first overview, but I will get into detail into these methods. So for this talk, I will first give a formal problem definition of the anomaly detection problem, then present these three main categories of models, our unifying view from this review, and then a selection of current interesting topics, and then hopefully give some hints towards where the field is heading. So, okay. To formally define what an anomaly is, so it's an observation that deviates considerably from some concept of normality. And if we want to formalize this, we have to specify two things. So what deviates considerably mean and what a concept of normality is. And the one main approach to do so is via probability theory. So we assume that there is some ground truth law of normality that describes our normal data distribution. That also has some PDF P. And then we can define the set of anomalies, so this deviating considerably by the region of low probability under this law. So everything that is below some certain threshold of this density. And this already leads us to the specific target or objective formulation, which is in anomaly detection, what we care about is the estimation of density level sets. So an alpha density level set is defined as the smallest high density region with some threshold tau alpha, such that a minimal amount of probability mass is satisfied. So for instance, if we have alpha density level set at a level of 5% intrusion for the standard Gaussian, then this would be the usual known confidence interval that goes from minus 1.96 to 1.96. And we sort of, by raising the threshold, of course, the probability mass decreases. And from all the sets that satisfy this minimal amount of probability mass, we take the smallest one. And the standard assumption that is made in anomaly detection is that this region of normality can be bounded so that it is tractable for estimation. And so there are various types of anomalies that are relevant in applications. Standard point anomalies would be individual points that are in this low density regions. So shown here in the upper left image, those individual single points that deviate from the majority of points. Group anomalies are a set of related anomalies, anomalous points. So for instance, here, a cluster of anomalies. So this is, for instance, relevant in network intrusion detection if you have similar types of attacks. Then what Stefan was also mentioning is what's relevant for time series anomalies is context, so contextual anomalies. For instance, given a context of time or context of space for spatial anomalies. And what's relevant here is that although the individual points in the series, they do not fall outside the normal region of the time integrated stationary distribution, they fall, they are anomalous in a given time context. And so, for instance, here a group anomaly would be a subseries or subsequence. And another important distinction, especially for choosing between shallow and deep methods, is the concept of semantic anomalies. Anomalies that are anomalous under some semantic concept. So for instance, here in the bottom right corner, the dog that is anomalous among the distribution of cat images. And this is only in a semantic feature space. But if we compare these images in raw pixel space here, so this white dog and white cat, they would be more similar than the cats among themselves. But on the other hand, there can be anomalies based on more low-level texture features as well. So for instance, here this cut in this fabric. So this is just a distinction that is relevant between choosing methods. Okay, and there are 3 related areas that deal with this type of problem, which are called anomaly detection, but also outlier detection and novelty detection. And in the probabilistic definition that I've just given, all of them are elements of this low density region, but they usually express different preferences or assumptions about an application. So an anomaly would be low density, a sample from a low density region, but that was sampled from a different distribution. So for here, for instance, the dog, an outlier sample from a low density region, but from this distribution. So here, for instance, a rare breed of cats, so this La Perm cat, or in the context of novelty detection, one often assumes that the normal data distribution is evolving or non-stationary, and there are novel samples from novel modes from this changing distribution. So here it could be a new breed of cats is the focus of modeling. But in the probabilistic definition, all of them are elements of this low density regions. And so on a high level, methods can take 2 forms. So detectors that are purely threshold based. So they yield a binary decision on an estimation if a sample is in this low density region or not. So if it's anomalous or not. Or what most methods do is that they derive some anomaly score, which is generally more informative, and of course from which always a threshold or a binary decision can be derived from some quantile, for instance. And to evaluate such methods, we have the usual binary confusion matrix. So our target would be to minimize both false alarms, so type 1 error, but also missed anomalies, so type 2 error simultaneously. And there's usually a trade-off that has to be taken into account in an application. And to have an evaluation that is independent of thresholds, one can consider area under the row curve or the precision recoil curve. And so the data settings that occur in the wild, the most common setting is that we just have a bunch of unlabeled data, which is the unsupervised setting, on which we have various assumptions about noise potentially, so measurement errors that generally increase the region of this normal data, or there can be some unknown contamination in this set. Another setting that can occur would be a semi-supervised setting, and here in the most general sense that we might have known normal samples, but also known anomalies that can be taken into account with some methods. And then a supervised setting, which is the most rare setting, where we would have confidently labeled normal and anomalous instances. And if the anomalies would have a specific homogeneous structure, this setting would not be different than just classification. But in some settings, so we could have some labeled anomalies, but still have the assumption that they are completely heterogeneous. So this, even if this is a rare setting, this should be always follow like a label-informed density estimation. But the major setting that we have in anomaly detection is this unsupervised one, of course. And the challenge, this is also the main challenge in anomaly detection, the unsupervised nature of this task, and the reason why, say, in comparison to other applications where deep learning brought advances way earlier, is that it's much harder to do deep learning in an unsupervised setting. And another challenge, of course, depending on the application, is to find a good representation for the problem at hand, balancing between false alarms and miss rate, noise and contamination. And to deal with these, there are different approaches how to tackle this. Scalability of the methods, both in the dataset size, but also in the dimensionality, where deep methods with SGD optimization and parallelization scale quite well. And of course, with more complex methods, there is the challenge of interpretability and explainability. So this is just an overview or introduction to the problem, and now we get to specific methods. And so, of course, as the formal problem would be the density level set estimation, one direct approach would be to perform density level set estimation through density estimation. So we from the data that we have, we estimate some density model, and then we could just plug this in to the density level set and compute an empirical p-value and then have a threshold detector. Or on the other hand, from the negative log likelihood, use this as an anomaly score. And this is like one of the main approaches that people take to do anomaly detection. That includes many of classic parametric models. So also in extreme risk settings, heavy tail distributions, but also histograms, kernel density estimation, and so on. And now the deep learning methods that go into this category. One category would be methods based on GANs. And what these methods do is so train on the unlabeled data, the generative model. And the first methods that use this for anomaly detection, they then, after training the GAN, they freeze the weights of the generator and then search for points in the latent space such that the reconstruction under the GAN becomes optimal. So after having trained this GAN, they use the generator of this model to derive an anomaly score from the reconstruction error under this generator for some test point. And this is what the ANOGAN by Schlegel has been doing, and also the ADGAN from Lukas Ruff. And more recent approaches, they also look at combined anomaly scores that take both the reconstruction error under the generator, but also deviations in the discriminator into account, because intuitively one would think, okay, because a discriminator discriminates between samples from the distribution and artificially generated samples, this would be suitable for anomaly detection. But in fact, after converging, this discriminator does not generalize well to like completely different samples that are not close to this distribution. But what those methods that use a combined score do, they take intermediate features of this discriminator and derive a score from there. Yes, and so this is not strictly a density estimation approach, but by training this generator, trying to approximate the data distribution, of course. And another class of models that you are probably very familiar with are variational methods, and especially variational autoencoders. And they have been used for anomaly detection pretty early. So by training them with a standard evidence lower bound, and then one can look either at this elbow, so taking both the reconstruction error or reconstruction probability and the KL divergence, term into account. But what people have found is that, at least for the VIEs, anomaly detection performance tends to be better when using, after training of a VIE, solely the reconstruction error under this variational autoencoder. An interesting recent work by Park specifically studies beta VIE, so where you can trade off between rate and distortion and make a connection there between methods based on reconstruction, so purely based on the distortion, and methods that only consider the rate, which would be one class classification methods that we will see in a bit. Another recent class of models that allow to do density estimation directly are normalizing flows. So where you have also the distribution of your data and then a very deep network where each individual layer is invertible, and thereby one can overall invert this transformation by the change of variables formula iteratively and train this directly on the maximum likelihood objective. And in order for the Jacobian there, in the change of variables formula to be tractable, they usually use specific forms. So for instance, triangular forms in these transformations. And an advantage of these models is that the likelihood can be computed exactly. And so this fits as a direct density estimation approach to anomaly detection. And this has been used, for instance, in physics or robotics. But one concern, or what has been observed for these models, so this is this third point here, is that some of these deep generative models, especially normalizing flows, they tend to attribute higher likelihood to out of distribution samples that are of simpler structure. So for instance, models that have been trained on fashion MNIST completely, and then if you look at the likelihood of MNIST digits in the standard formulations, they tend to assign higher likelihood to such models. And there's some very interesting work in this direction, analyzing this further and observing that likelihoods in such deep generative models, they are often still dominated a lot by low-level statistics. And so this class of models, they give a very informative ranking. So you have a full score for the samples, but by this they are also the most costly in terms of samples required, because if you go for a full estimation of the distribution or the density, implicitly you estimate all of the level sets. And another remark, so density estimation is also the main approach to time series anomaly detection, where you perform or learn forecasting models, and the forecasting error can be used to indicate anomalies. And so what the next class of models, one-class classification models, try to do is in the spirit of Wapnick's principle. So if you try to solve a specific problem, you should try to avoid to solve a more general problem. So here, density estimation or learning a generative model as an intermediate step. And so the idea of one-class classification is to directly learn a discriminative model that encloses this high-density region of the normal data. And we can think of it conceptually as a very tricky binary classification task. So here, the standard binary classification risk, but we usually don't have any samples of the negative class, so of our anomalies, which is why we require some specific regularization or additional learning objective to minimize the miss rate. And classic kernel methods doing this are the very well-known one-class SVM and support vector data description. So one-class SVM fits a max margin hyperplane in the kernel feature space, and the support vector data description minimum volume sphere. And for these estimators, it can be shown that they're indeed consistent new density level set estimators. And they're based on this minimum volume principle. Yes, but of course, do not scale well in the dimensionality of the data. And so one of the approaches that we worked on is so deep one-class classification, and especially the deep SVDD method, which formulates this idea for neural networks. So to have this minimum volume enclosing sphere in the output space and learning the neural network on this objective, aiming to fit most of the data in a very small space, and by this detecting anomalies by falling far away or outside of the space. And based on this approach, there have been a lot of follow-up works for different applications and also multi-sphere formulations. But there's also some models that are based on hyperplane formulations. So for instance, from Alfani and Kalapati, that are closer to the one-class SVM. And one of the key problems or issues to solve with this type of model is to regularize against a trivial solution, because the objective would be perfectly solved if we map everything into a point. So one has to think about meaningful regularization for this type of model. And there are also various solutions proposed for this in the literature. So for instance, keeping also a reconstruction error, or having the embeddings freeze. So for instance, in NLP applications, this has been done, or some penalization on the variance, so inversely, or if there are if one can think of or use negative samples, either created artificially or from some auxiliary corpus, or actual anomalies. This can be used to avoid this collapse, or also pseudo-labeling and the self-supervised approaches, or incorporating some manifold structure into the data that preserves some structure in the feature space. And so the third major type of approaches are reconstruction models, and they are not necessarily motivated in a probabilistic fashion, but rather are based on the principle that we want to learn some data encoding model that is trained on the normal data, so that when we have some anomalous samples, this is not as well reconstructed as the normal data that the model has been optimized on. And for these types of models, there are two principal assumptions underlying them. So one is a manifold assumption, and the other one is the prototype assumption. And for the default reconstruction baseline or model, of course, is PCA, and there are several variants of PCA, robust or kernel PCA, also probabilistic formulations and Bayesian formulations that again provide a link to density estimation. Then deep autoencoders of various flavors, which are the dominant type of model that is found in the deep anomaly detection literature, where one can incorporate some manifold assumption into the model, so mapping to some or embedding the data on some low dimensional space. And methods following the prototype assumption, they assume that the data can be described by some discrete set of points. So k-means would be an example of this, or vector quantization, and also deep clustering methods, which for them, the decoding step would be identifying some nearest prototype, and the reconstruction error then the distance to this type of prototype. So this allows us to consider these types of clustering methods also as a type of reconstruction model. So, and having identified the models in this way, we can see them based on these common principles, as I've shown in the outline in the beginning. So the one-class classification methods that take a discriminative approach, trying to estimate this density level set directly. Then the probabilistic or density estimation methods and reconstruction methods. And so apart from those two dimensions, so the model dimension, where we have specific either density models or hypersphere or hyperplane model, and the feature map, we in this review do identify three more dimensions, which are the loss-specific types of regularization and the inference mode. So if it's a classic frequentist or latent Bayesian or fully Bayesian approach. And this allows us to categorize these methods in a systematic manner. So to see the differences and similarities, but also potentially what new directions arise from this. So here in this big wall of methods. And another result is so that there is no Eierlegende Wollmilchsau. So there's in the spirit of all model song. So Eierlegende Wollmilchsau means an egg-laying wool pig that also gives milk. So there's always a trade-off, of course, between the different models. And so here shown detection performance on this MVTech anomaly detection data set, which are images from visual inspection for different types of objects or also textures. And we can see, so it no single method dominates over different ones. Okay, and now moving to some recent topics. One idea we've been working on is to formulate a model for the general semi-supervised anomaly detection setting, so where we also have some labeled anomalies available. And so in the literature, a lot of methods that are termed semi-supervised, they consider the case of unlabeled and positively labeled data. But in many applications, one also has some labeled anomalies sometimes at hand. So for instance, failure cases verified by some expert, or specific diseases identified by some doctor, for instance. And so the method that we presented this year at Outlier, the deep SAT method, is based on the deep SVDD method for normal data. So we again want to learn this our neural network, so to map everything to some sphere of minimum volume, but for the known and labeled anomalies to map them outside or far away from the center of the sphere. And just showing the results on one of the common benchmarks, which is considering classes of CIFAR 10, always one of the classes to be normal and all of the other classes to be anomalous, and then iterating over this one versus rest setting, one can see that even having only 1% of labeled anomalies in the training set gives a significant boost to this semi-supervised methods. And that in this case, a standard classifier is vulnerable to overfit only to the known types of anomalies. So the crucial part, again, in formulating such models is to for them to generalize well against to generalize well for the towards novel types of anomalies. So accounting for the heterogeneity of anomalies. And the idea behind the deep SAT method is, so by penalizing points inversely to be away or outside of the sphere, to not impose any concentration assumption on the anomalies, so that they don't have to have similar structure. Another very interesting idea is the idea of outlier exposure from Dan Hendrycks and Tom Dittrich, which is that in some domains, to make use of the massive amounts of publicly available data as auxiliary negative samples. So for instance, in computer vision, ImageNet or public stock photos that are available in NLP, Wikipedia, or large book corpora, or for intrusion detection, there are also very many public system logs repositories online. And the idea behind this is that we have a more informed domain knowledge. So even if those outlier exposure samples do not correspond to ground truth anomalies that we see, they help to improve the characterization of the normal data distribution that we have, and sort of provide a more informative exposure distribution than, say, just artificial noise. So about the distribution of natural images, for instance, or the English language in general. And this has been used exactly in these domains already and has seen some significant improvements. Another idea or class of approaches is self-supervised models, which aim to learn a characteristic representation of the normal data distribution by solving some auxiliary task. And this is a line of research that is considered for representation learning in general, but there are some specific works looking into this for anomaly detection, because the appeal, of course, is self-supervision. Self-supervised models, they also learn in the absence of labels, which makes them especially interesting for anomaly detection. So examples of such auxiliary tasks are, for instance, trying to predict what kind of transformations have been applied to images, so rotations, translations, and so on, or future frame prediction in videos, or what those language models are doing is to either predict masked words in some sentence or predicting next sentences. And this has been used in visual anomaly detection by Golan and Eierlegende, and also Hendrycks and Wang, where classifiers are trained on predicting these transformations, and then an anomaly score can be derived from after training such a model. One can look at the softmax statistics, and the more certain this is under these transformations, the more normal a sample is. And on the other, because it has been optimized on the training data, so finding, for instance, specific symmetries that are apparent in the normal data. So if this classification under the transformation works well, this is indicative of a sample being nominal. And this has been recently, or also this year at Outlier, been extended to random affine transformations to general types of data by Bergman and Roschen. And of course, the overarching question for these types of approaches is to what extent self-supervision can facilitate to learn semantic representations. Another interesting topic is explaining anomalies or interpreting such models. And there, together with Jakob and Grégoire, we had some work on layer-wise relevance propagation for explaining anomalies, which is a method originally developed for supervised deep models that starts from defining the output as like unit 1 of relevance, and then distributing the relevance back by specific rules that aim at linearizing the model at each individual layer, thus finding always the inputs that most explain the output, and then tracking this back to the pixel space. And by this way, we can highlight or show those input features that are most relevant for the anomaly score. And by this, by formulating many classic methods in this type of way, so having them as first as this type of 3-layer neural network, where we first have a feature extraction, and then a distance computation and a pooling. This allows us to apply or use layer-wise relevance propagation for a broad range of models. And so here is an example again of this wood panels where there are some holes and scratches on the wood, and we can see here on the second image the ground truth and the explanation for various methods. And what's interesting there is if we look at the pure detection performance, so here in the left table, it seems to indicate that kernel density estimation for this data set is best in terms of detection performance. But because for this data set we have the ground truth anomaly segmentation heat maps, we can look at the accuracy of the explanation as well. And there we see that the KDE is worse than the deep model. And so this is what's called a clever Hans effect. So the model yields the correct prediction, but based on the wrong features. And we can see on the next slide that in fact for these wood panels, there in the test set samples, there is a systematic, stronger wood graining that KDE picks up on, because in this high-dimensional space, KDE effectively just looks at the distance to the mean. So this is one reason why interpretability of such methods and explaining them is crucial, because just looking at pure detection performance score can be misleading. And what is interesting here is that this type of behavior is, because these are unsupervised models, is purely based on inductive biases of the models that we have. So in contrast to, say, the clever Hans effect in supervised models, where a deep model picks up on some spurious correlation in order to optimally separate the labels. Here, this is purely based on the structural or inductive biases, structural assumptions or inductive biases that we have on the models. And one thing one can do is to bag different types of structurally different models to overall achieve a more reliable detector. Okay, and so to conclude, some open challenges and potential future research paths is further improving interpretability and trustworthiness of such anomaly detectors, because so one can think of anomalies also that are anomalous not due to the presence of anomalous features, but due to the absence of normal features. So for instance, if we train a model on MNIST and we show a completely black image, what should an explanation of why this black image is anomalous look like? Because we can't so with these types of relevance methods, we can highlight anomalous features. But if it's due to the absence of normal features, this is a trickier interpretability or explainability problem. Another thing from this unified view is that there are also, or this is revealing combinations of these various modeling dimensions that have not been explored. So for instance, ideas that have been explored with traditional methods, so specific robust models or active learning strategies, for instance, where we can transfer such ideas between the models. Then there's also a desperate need for new and challenging data sets. So a large part of the literature still considers or repurposes classification data sets in this one versus rest or leave one out fashion, which is okay to some degree, but of course, having data sets with actual anomalies would help to better test and evaluate the methods that we would develop. So for instance, like this MTech anomaly detection data set. Another thing is that anomaly detection is also related to other lines of research in robust deep learning in general. So for instance, out of distribution detection, where the focus still is more on classification, but having a classifier that detects, so while classifying the known classes accurately when some new sample deviates from this. So in this setting, we have some additional information which would be about the in-class distribution or in-class labels that we have. but also to open set recognition or adversarial attacks, which might be considered extremely hard anomalies. And then also on the theoretical side, having seen this clever Hans effect, this is the issue theoretically of out of distribution generalization and how to control that. Then what's also interesting is, so the definition we used here for anomalies is based on low density regions, but in truly high dimensional spaces, what can happen is that there's more probability mass in regions where there is not the highest density. So for instance, for a Gaussian distribution, the probability or the most likely regions tend to be on this annulus. And from this, there are novel ideas how to formulate the anomaly detection problems for truly high dimensional problems theoretically. And yeah, for representation learning, for anomaly detection, looking into an information theoretic perspective. So for instance, this trade-off between rate and distortion, which I think is an interesting link between one-class classification and reconstruction models. And yeah, so for the methods that I presented, we also have the code open source available. And with this, I would like to conclude my talk. So thank you very much.
All right, Lukas, thank you very much. That was a great presentation. So I'm sure we have a little bit of time for questions still. And I'm not sure if people can just speak up, or if otherwise, you know, they can just type their questions into the chat and I will read them. So maybe to kind of start with one question from my side while people think. What is actually the true benefit? I mean, if you compare the deep one-class anomaly detection method to, say, just using a variational autoencoder and thresholding according to probability. I mean, this looks pretty related in some sense.
Yes.
Can you give an intuition why one works much better than the other?
So I think what's interesting there to compare is where you derive the anomaly score. So for most of the reconstruction methods, you finally derive an anomaly score again in the original input space. So for instance, pixel-wise reconstruction versus for the deep one class, you usually do this in the higher level latent space. And I think this is relevant in terms of the type of anomaly that you're detecting. So my intuition there would be that so for semantic anomaly detection, it is more relevant to do or derive the score in this higher level feature space than deriving the score from the original space. So for instance, from one experiment that we did is with ImageNet, also this usual one versus rest setting, where one of the classes is considered normal, and then against I think 29 other classes it is for this benchmark, considering them as being anomalous. And for the deep one class, the semantic anomaly detection performance there was much better for, say, something like a reconstruction model, because just the variation in the normal data was so great that for the reconstruction model, you got also very well good or like blurry reconstructions, but on this variation of the data in general, which wasn't very indicative for some semantic concept that we had. But the difficulty with the deep one class is what type of training or auxiliary training objective that you use it with to foster such semantic representations. So you can start with some pre-trained network, for instance, or look into the self-supervised ones to improve this. But I think the interesting difference is where you derive the anomaly score and what is relevant for your application, I would say.
Mm-hmm. Okay, thank you. So there's actually one question here in the chat by Shu. The question is, for any model for anomaly detection, how to select the model to test? Especially in unsupervised methods, I assume that there is not a validation set. Then how to get the good model to test? For example,
Yes.
Gaussian mixture models have some hyperparameters. How to tune Gaussian mixture models?
Yes, that's a good question. So for the density estimation methods, actually, what you can do is look, for instance, also at the likelihood of some validation set. So if you think of standard, just to give an intuition, standard kernel density estimation, what you can always do is look at the fit of also some unlabeled normal data and select the model this way. But I think in applications, what helps is if you do have some few labeled anomalies, you can improve detection there as well. But other than that, I agree, like this is always an issue in the completely unsupervised setting. But what you can do is to look either to look at the error of the model on some unlabeled or normal data set to do part of the selection.
Mm-hmm. Any more questions? Yeah, so Nicholas asked a question here. For the chart where you have break it down by deep, shallow, and the type of model, classification, probabilistic, reconstruction, distance, are there no deep instance methods, like metric learning with CME's neural nets, etc.?
Yes, so this would be where there's this white space here, right? So we've looked into this, and actually, so I know that there are some deep metric learning works, but I haven't come across works that so far that have considered this for anomaly detection. So maybe there's some work to do, or there it did so far not work well. I'm not sure about that, but I agree that this is like an area that'd be interesting. Yes.
Mm-hmm. All right. Maybe one last question by anybody? So if that's not the case, then thank you very much, Lukas. It was really great to have you here. And